Hello, this video explains some of the tools Plumed has for probing local order. These tools are useful when it comes to examining solids and liquids near coexistence, or when you're examining the interface between a solid and a liquid. Basically, they can be used to tell us the parts of the simulation cell where the atoms are in a solid-like configuration, and the parts of the simulation cell where it is in a more liquid-like configuration. This is useful when one is trying to determine the size of a crystalline nucleus or a critical nucleus during a simulation of crystallization, or when one is trying to determine the precise location or the extent of the interface between a solid phase and a liquid phase. Let's start this introduction by revising some concepts from other videos. Hopefully by now you are comfortable with the notion of a symmetry function, and that a symmetry function, this is a concept that has been discussed elsewhere, but a symmetry function is a function that takes each atom in the system, calculates the set of vectors connecting said atom to all the remaining atoms in the system, and then calculates some function of that set of vectors. The simplest such function we can calculate is the coordination number. This measures the number of atoms that are within a certain cutoff distance of the central atom, the number of atoms in the first coordination sphere, if you will. What this function does is illustrated on this slide, and the manner it is calculated using plumed is shown below. In this first calculation, we are calculating the coordination numbers of the two red atoms. We are then using Plume's multi-Colvar functionality to calculate the number of coordination numbers that are more than 4. This is the case for both the red atom labelled number 1 and the red atom labelled number 2. For both these atoms, the coordination number is 4 or greater. As such, the quantity calculated by this command is equal to 2. Changing this input slightly, we can calculate the coordination numbers for all of the atoms in this system and can once again calculate how many coordination numbers are greater than 4. Let's now consider something slightly different. This figure shows once again the positions of a set of atoms or molecules. In the video on Steinhardt parameters, we learned how that we could calculate a vector quantity, the Q6 vector, for one of the atoms. Much like the coordination number, this quantity, the Q6 vector, is a symmetry function. It is a function of the set of vectors connecting the central atom to all the remaining atoms. However, unlike the coordination number, this quantity is a vector. It is a number with both magnitude and direction, as illustrated in the figure. Let's now suppose that we calculate this quantity for all the blue atoms and for all the purple atoms. We can do this with the two commands shown here. What we now have is a set of vectors that are each located at a discrete point in space, namely the position of the atoms. Because each vector is located at a particular point in space, we can calculate a coordination number for the central vector as shown. So we first calculate the distance between the central vector and all the other vectors, and then we introduce a cutoff. When calculating the number of neighbours for this central vector, we can further insist that a particular pair of vectors only contributes 1 to the sum if those two vectors have the same orientation. We can do this by exploiting the definition of the dot product of two vectors. In the example shown here, the coordination number is 4. There are 4 atoms within that cutoff distance of the central vector. However, only 2 of the vectors in the first coordination sphere point in the same direction. The other two vectors point in directions orthogonal to that of the central vector. As such, our modified coordination number is only 2. The calculation described here can be done using the nlinks command that forms part of plumed 2. Furthermore, the vectors on the atoms do not have to be the Steinhart parameter. They could also be the direction of a particular bond in a molecule, the orientation of a molecule, or any other vector quantity. Let's now suppose that we want to calculate a distribution of such quantities. In other words, let's suppose we want to do what we were doing with the coordination numbers, but with this new quantity that takes into account both the distance of the central vector from the surrounding vectors and the relative orientation of these vectors. Once again, we can use the Steinhart parameters, or any other vector calculating action, to calculate a vector located on each of the atoms in the system. Here we have tagged 2 red atoms and are examining functions of the distribution of these 2 orientation-dependent coordination numbers. As we did with the simpler example on the previous slide, we first introduce our switching function on the distance. And we then use dot products of the relative orientations of the vectors in order to determine the number of vectors in the first coordination sphere of the central vectors that have an orientation similar to that of the central vector. The final value for this quantity is 3 for the red atom on the left and 2 for the red atom on the right. This is unfortunate, as the quantity that we are calculating with the command shown here is the number of these quantities that are greater than 4, which in this case is sadly 0. Both of these quantities are less than 4. The advantage of this local Q6 command over nlinks is that this is once again a multi-Kolvar. In fact, it is a really rather complex symmetry function. Because of this fact, we can do all the things that we could do using the coordination number with this much more complex quantity. In other words, we can calculate the average, the number of values less than a target, the number of values more than a target, and so on. A similar and related symmetry function can be calculated using the local average command. Similarly to local Q6, to calculate this quantity, you have to use some plumed action to calculate a vector quantity centered on each atom. Once again, this vector could be one of the Steinhart parameters, the internal orientation of a molecule, and so on. Once this is done, you then establish which atoms are within the first coordination sphere of the central atoms. Things differ from local Q6 from here on. In local average, you add together all the various vectors to get a final measure of the local degree of order. Obviously, if all the vectors point in the same direction, that is to say if the structure is ordered, the final vector you obtain is rather large. By contrast, if the structure is disordered, then you will have many vectors pointing in different directions. These vectors, when added together, will give a final result that is rather small. It is thus the norms, i.e. the lengths of these final vectors, that are used when calculating the more than function in the final multi-Kolvar shown here. In the 2 examples I have shown in this video, I calculated these quantities for 2 particular tagged atoms in the system. This was mostly to keep the pictures simple. In many applications, you will want to calculate local Q6 and local average for all of the atoms in the systems. If this is what you want to do, then you should use the commands with the following form. Thank you for your attention.